Espero se encuentren bien. Bueno, I would like to introduce here today's speaker is Wolfram Bauer from Leibniz University in Hannover, Germany. He will speak about Berger Coburn theorem, localized operators, and the Toeplitz algebra. Normally, he is a global expert in Toeplitz algebras. Right now, I know him also for working in manifolds, and well, there are many topics. So if you have any question, please go ahead with him. Please, Wolfram.
Yeah, thank you very much for the nice introduction. And yeah, I'm very happy to be back here. I do not remember how many times I have been at Sinverstuff, but at least 3 times, I think. And it's very nice to be back here, see many familiar faces. And thank you very much for the invitation, especially to Igor. And yeah, so today I want to talk about Toeplitz operators and algebras generated by Toeplitz operators. And I want to start with a, these days maybe classical theorem, which is the Berger Coburn theorem, and use this to discuss these algebras. And this is a joint work with Robert Fulce, who used to be in Hannover, and Miguel Rodriguez, who is here. So together with them, we have some applications of this stuff. Okay, so this is my plan. I start from the beginning. I will tell you what are Fock spaces. These are p-Fock spaces, and what are Toeplitz operators, even so I assume that most of you know this very well. And then I explain the classical Berger Coburn theorem, which deals with Toeplitz operators with unbounded symbols and gives the criterion when these operators are actually bounded. This has been proven in the 80s, I think, using pseudo-differential operator calculus. And here I want to present a rather simple proof, just using, in a way, interpolation or the Schur test. And it's just based on operator theory on the Fock space. So there will be no pseudo-differential operators. And it has the advantage that it generalizes to other spaces and will also be useful later in the proofs. And the next topic, which seems a bit unrelated to the first one, is the Toeplitz algebra. This is a C-star algebra, which is generated by Toeplitz operators in this framework of Fock spaces. And I want to present a list of characterizations of these algebras, which partly do not use the notion of Toeplitz operators. And then the question is, what actually is that Toeplitz algebra? What is actually inside and what is not inside? I'll give you some examples. Okay, and so this is the starting point. What we do here, I want to consider Toeplitz operators on p-Fock spaces. And then I pass, in the case where p equal 2, we are in the Hilbert space setting, to C-star algebras which are generated by those. And this topic, there are a lot of tools which go into this topic. The Berger Coburn theorem, as I told you, rely on pseudo-differential operators, even so they do not play a role here. There is a thing which is called quantum harmonic analysis, which is specific to the Fock space setting and gives nice results in a short way. Also, this will not play a major role here. And correspondence principle is a principle which connects operators and symbols and the correspondence with between these two things. So the spaces are spaces of entire functions over the complex n space, Cn, and then there's also a parameter which is denoted by t, and you may think of this as a time parameter maybe. And what we do is we fix a family of Gaussian measures, which is parameterized by this t here on Cn. And then we form spaces from these measures. So if p is between 1 and infinity, then we can look at the LTP spaces. So this is just the usual LP space over Cn with this measure here. And what's important is that in the parameter of this measure, the p already appears. And then if p equal infinity, then we have the space L infinity t, which is defined by a subnorm or essential supremum of G, but we have to multiply this with this Gaussian weight here. So to include also holomorphic functions which are not constant, for example, unbounded holomorphic functions. And what is the p-Fock space? This is just the intersection of these LP spaces with the holomorphic functions on Cn, and that gives us a new space. The notation is FTP. And that now is defined for p between 1 and infinity is included. And the very classical case, of course, is where p equal 2, then we have a Hilbert space. So here are some standard facts about these spaces and the operators we may consider on these spaces. So these are the Toeplitz operators. So what is very classical is when p equal 2, then we have a family of Hilbert spaces parameterized by t. And these are reproducing kernel Hilbert spaces. And the reproducing kernel is very explicitly given by this Gaussian, where the t appears here in the denominator. So reproducing kernel Hilbert space means that whenever you fix a point in Cn, you fix a point in this 2 Fock space, then the point evaluation is just given by an L2 inner product with this kernel here, this kernel in the second component. So this reproduces the point evaluations. And then what is also very well known is that there is an orthogonal projection from the L2 space to the Fock space, which then depends also on the parameter t. So this is my notation, pt. And it's just taking a function, an L2 function, and pairing it with the reproducing kernel here. And we may also write this as an integral operator in this form. And that's an orthogonal projection in the Hilbert space setting. But we can also consider this on the p-Fock space. So we consider this integral operator here as an operator on the p-Fock space, and it is very well known that that is still a projection and it is bounded from LTP to FTP. Okay, on these spaces, now we consider Toeplitz operators. What are Toeplitz operators? These are operators of a very simple form. So we have a multiplication MF with a certain symbol. On Cn, the symbol is measurable, but it may not be bounded at the moment. And then we project back from the L2 space to the F2 space. And since both operators are bounded on the FP space, we can also consider this as an operator from FTP to FTP. And as I said, the symbol might be unbounded, which then results in unbounded operators. So we have to say something about the domain. And I always want to assume that the symbol is not growing too fast at infinity, so that the operators are still densely defined, which means that this domain here of all FTP functions such that the product still is in LTP is a dense domain. And it contains, for example, all the reproducing kernels for the with the fixed second component. This is a kind of quantization which takes a symbol and assigns to this an operator. And since we have a reproducing kernel, there's also a kind of inverse quantization which takes an operator and assigns to this a symbol. This is the Berezin transform, which can be defined, for example, if p equal 2. So we start with a bounded operator on the 2 Fock space, and then we apply the operator to the normalized reproducing kernel. This is a small k set t. It's the normalized reproducing kernel, and we pair it with the normalized reproducing kernel in the inner product. That produces a function, and that function is a bounded function if that operator is bounded, but you may still form these quantities for unbounded operators as long as this one here is in the domain of the operator, and that's called the Berezin transform, and it also depends on t, so it's a parameter family of functions. And so what happens, for example, if I choose, I put a to be tft, so a Toeplitz operator with the symbol t, and I assume that the symbol is not growing too quickly at infinity, so that these products are still L2 functions. And then it is well known that this Berezin transform of this Toeplitz operator, which is also denoted by f twiddle of t, which is this one here, is basically the heat transform. So it's just convolution with the Gaussian kernel. And this may, depending on the growth properties of f, this integral may only be defined for small values of t. You see if t is very small, then that's very big, and it might be integrable, but if t becomes very big, then the integral may not exist anymore. So I want to assume that at least for small values of t, this integral here appears. So this is the heat transform. So the heat transform has, of course, a very nice property. It's a semigroup. So this assignment from t to f twiddle of t is a semigroup by this reason here. So if I add 2 parameters, then since it's the semigroup, it's the exponential of the Laplace operator. So this is the heat operator, basically. And that splits into 2 parts, which gives you this semigroup property here. And that's very particular for the Fock space. And now the question is, if you have a Toeplitz operator with, let's say, an unbounded symbol, then the question is, when is that operator bounded what is the criterion on the symbol. And the Berger Coburn theorem gives some answer to this, which is not complete, but it's very useful. And it says this: if you have a symbol, an operator symbol, which is L2 function, so it could be very unbounded, a polynomial or something like this, on the complex n space, and then you look at the Toeplitz operator, in the case where p equal 2. And then there are two estimates. If you take a parameter s between 2t and t half, t is fixed, then you can bound the heat transform, the supremum norm of the heat transform, by a constant times the operator norm of the Toeplitz operator with this symbol, f here. And if s, the parameter, is small, meaning between 0 and t half, then you have the converse inequality. So you can bound the operator norm by the subnorm of the heat transform of f at time s. So this tells you, gives you a criterion on the boundedness of the operator tft in terms of the heat transform of the symbol f twiddle s. So if f is an unbounded symbol function, then it may happen that after some time in the heat flow, the solution or the heat transform produces something bounded. Okay, and then even if you start with an unbounded symbol in the operator, you may have a bounded operator. So these constants which appear here, they are somehow universal. You can estimate them. I'll give you some formula. Maybe they depend on st and n, but nothing else. And this is an old result by Berger and Coburn from the 94th. And what he basically did, they take the Toeplitz operator, and there is a well-known Hilbert space isometry between L2 functions on R, on the real line. This is the Bergman isometry. And if you conjugate the Toeplitz operator by the Bergman isometry, then you produce a pseudo-differential operator on L2R. And boundedness of the Toeplitz operator results in boundedness question on pseudo-differential operators. And you know what the symbol is. And then you have the Calderon-Vaillancourt theorem, which gives you the answer in a way. And that works well if p equal 2. So this is what you should keep in mind. If you have a Toeplitz operator with an unbounded symbol, then you can control the operator norm for small values of s by the heat transform of the symbol. And conversely, for large values of s, large meaning bigger than t half, the operator norm controls the heat transform of s. And the question is, of course, what happens at s equal t half? And the conjecture is the operator, Toeplitz operator, is bounded if and only if the heat transform at the time s equal t half is bounded. And that conjecture has been around for a long time. And I think 2 weeks ago, Coburn sent me a paper saying that he found a counterexample. So that's probably not true. But the counterexample is not so simple. So one has to check it. So what I want to do is here, I want to give you a proof of these two inequalities, which are crucial. And one inequality is rather simple to prove. I give you the idea. The other one takes a bit more effort, but both ideas are maybe clearly understandable, I would say. So how can you prove the first inequality? So you want to have an inequality of the heat transform of the symbol by an operator norm of the Toeplitz operator if the parameter is small, is large, between t half and 2t. So we are in the right region of the picture before. And the idea is this. So Coburn and Berger, they constructed a family of trace class operators depending on the point set. So set is in Cn. And depending on the value of s. And trace class with bounded trace, bounded in the parameter c, such that this heat transform can be written as an operator trace of the product of the Toeplitz operator with this family. So this can be constructed. And then what they do is they use just the standard trace norm inequality. So they use this very standard fact that the trace of two operators, one bounded, the other trace class, can be estimated by the operator norm of the first one and the trace norm of the second one, and you can just apply this to this thing here, and that gives you the result. Okay, so this gives you the operator norm of the Toeplitz operator here, and the supremum norm of these trace class operators, which are bounded uniformly in set, and that gives you the constant. That's all. So this doesn't use any pseudo-differential operators, just that simple inequality is behind. The other one is maybe the more interesting one because it gives you a criterion on the boundedness of the operator. And this works like this. So we can look at the Berezin transform of the symbol f of the operator. And the Berezin transform, if you remember, was taking f, multiplying with the reproducing kernel, the normalized one, and taking inner product with the normalized reproducing kernel at the same point, z, z. But we can extend this to different points, z and w. So this is sometimes called a bivariate Berezin transform. So you extend this to two variables. And this new function basically can be used to define a new integral representation of the Toeplitz operator in terms of this function. So this function has all information on the operator since the Berezin transform is injective. And the new integral kernel, which gives you an integral form of the Toeplitz operator, is this one here, where this function appears. And the proof is also not very difficult, so we only have to do this in the case where p equal 2. So what we want to do is this. We want to evaluate TFG at the point z, and we use the fact that we have a reproducing kernel, we write this to the inner product, and then we put the Toeplitz operator as an adjoint operator to the other side. And then we just calculate that kernel here, and that's this kernel. This is a calculation. So we calculate TFT star applied to KZT. That gives you this kernel where this function appears. Okay, this is basically the calculation. But this is in a way nice because it relates the operator to the heat transform in a more direct way and not just to the symbol itself. And now we have the semi-group property of the Berezin transform. This is that function on the diagonal. This comes from the fact that the heat transform is behind everything. And this semi-group property only works on the diagonal, but it should have some impact to the function I showed you before, ft twiddle zw off diagonally. So the question is, how does this semi-group property translates to off-diagonal values of the Berezin transform, to these functions? So what does it mean for this function here? And more generally, can we in a way calculate this function here if we know the heat transform of f at an earlier time on the diagonal? We want to extend this off-diagonally. And the answer is yes, it must be possible because all information on the operator is in that function and also in that function, so there must be a way to come from one to the other, and here's the formula. So if you pick two values, z and w on Cn, and you take a time before t, and then you can obtain this heat transform extended to off-diagonal values by some exponential function here, and then you take the Berezin transform or the heat transform at time s, this earlier time, in an inner product with these two functions here, and that is the L2 inner product corresponding to the parameter t minus s. And this in particular tells you, if you know that this function here, f twiddle s, is bounded, then Cauchy-Schwarz inequality gives you this, gives you such a bound. And also the proof is not so difficult. In a way, it is a off-diagonal extension of the semi-group property using analytic continuation and some integral estimates. So there's nothing deep behind, just you have to extend and use the fact that things are analytic, and you only need to know things on the small set to extend to off-diagonal values. Okay, but what does this tell you? So here, a certain number in the exponent appears, which depends on t and s, and if this number is negative, then this right-hand side has an exponential decay and is very nicely bounded. And this number negative precisely means s smaller than t half. And this is the condition in the Berger Coburn theorem. So precisely when s is smaller than t half, this is negative. And so this is in the way the main idea. And now I just tell you what is a small extension of the Berger Coburn theorem to the case where p is not equal to, and where these estimates are basically used, and some interpolation also. So the extension of the previous result is this. If you have a symbol f, which might be unbounded, and if you observe that the heat transform at time s smaller than t half is bounded, then the Toeplitz operator with that symbol is bounded. It's expressed in this form here, as we saw, and it's a bounded operator. And you can actually bound it by a constant, which is universal, depends on t, s, and n, and the subnorm of the heat transform at time s. So this is the control of the operator norm by the heat transform for small values of s. But this works not only for p equal 2, but any p. And so what's the idea? So we can check this in the case p equal 1 and p equal infinity. In one case by a direct estimation, it's rather simple. In the case p equal 1, you have to use these inequalities, which I just showed you. And then you can just do complex interpolation, and you get all the values in between, knowing that these p Fock spaces also interpolate in the expected way. So that's the proof. If you are only interested in the original case where p equal 2, you can also forget about the complex interpolation and you use the inequality and the Schur test. So in the way, everything is the Schur test. Okay, there is one extension which might be interesting of this result to what I call Toeplitz operator on large vector valued Fock spaces. So these are Fock spaces of entire functions which have values in a Hilbert space themselves. And then the symbols of the operators are not functions, scalar valued functions, but operator valued functions. And these operator valued functions might be also unbounded, and you may wonder when is the corresponding operator bounded, and you can precisely, at least in the case p equal 2, generalize this to this setting. Okay, there are here a few remarks. There is a constant which appears in the estimate, and one sees from the calculations that that constant actually blows up if you approach with s the critical time, t half. And the rate of blow up is just what's written here on the slide. A bit more general question, which also has been treated, is the question when is a product, for example, of two Toeplitz operator, not a single Toeplitz operator, but a product of two Toeplitz operator, when is that bounded? If the symbols f and g are unbounded, that's a bit different question. Even so, such products in many cases can be reduced to just a single Toeplitz operator where the previous theorem applies, but you may ask more general questions. And then, as I said, what happens actually at the limit case where both inequalities meet, which is the case s equal to t equal s half. And as I told you, conjecture was boundedness of the operator if and only if heat transform at that time is bounded, but that seems to be not the case. So here's another result, which gives you a bit better criterion. And this is the case where the symbol is in BMO. BMO means bounded mean oscillation. So that's a condition on the symbol, on the oscillation of the symbol. Functions of bounded mean oscillation could be unbounded on Cn, but they have not too big growth at infinity, but they can be unbounded. And in this case, one can show that the heat transform of such a symbol is bounded for one time t if and only if it's bounded for all times. So what is always true, if you observe that the heat transform, let's say at time t is bounded, then it remains bounded for all larger t's. But it may happen that it is bounded at some time t, and then at earlier times it was unbounded. So this can happen. If you have a function in BMO, then this never happens. If it's bounded at some time, it's also bounded, it has been bounded before. And this is somehow useful because then you have both estimates at the same time for BMO functions. So in particular, such an operator is bounded if and only if f twiddle t half is bounded. So in this case, this Berger Coburn conjecture is true, actually, for these very specific symbols. So now I want to pass to operators with bounded symbols, and not just the operators, but I want to say something about the C-star algebra, which is generated by these operators. So I want to start with a very old result by English, and now we are only in the Hilbert space setting, so p equal 2 from now on. And English observed this. If you have an operator, a bounded operator on the Fock space, and if this is a finite sum of finite products of Toeplitz operators, and these operators have essentially bounded symbols, then the Berezin transform of this operator tells you something about compactness. So it says that such an operator is compact if and only if the Berezin transform, which is this function here, some kind of inverse quantization, vanishes at infinity. So compactness is just captured by the behavior of the Berezin transform at infinity. And the natural question is whether this effect really has something to do with the assumption that A is a finite sum of finite products of Toeplitz operators. So maybe that's very specific somehow. So one may ask whether this generalizes to a larger class of bounded operators, or maybe it's true for all bounded operators. because the Berezin transform really is an injective map, so it has all the information of the operator A inside. And here's some first generalization of this, which uses the notion of operators acting on a scale of Hilbert spaces. And the idea is this, so from now on the parameter t is just fixed, it doesn't play a big role here anymore. We are in the setting of a Hilbert space, p equal 2. And I want to construct inside the Fock space an increasing scale of Hilbert spaces, and I want to look at operators which act on this scale in a certain way. I will explain what that means. So to construct these Hilbert spaces, I take an increasing sequence of real numbers, which is inductively defined in the following way. So C0 is just 0, and then Cn plus 1 is 1 over 4 times 1 minus Cn. So this is just a sequence of reals, of positive numbers, and one can easily check it's monotone increasing, and these Cn's are always smaller than 1/2. And with this sequence, I can now build a scale of spaces, Hilbert spaces, or here we have maybe just a Banach spaces. So I define a norm by taking this weight function here, where the Cn appears in the exponent, and then I take the essential supremum of a function f. And HCn is now the space of holomorphic functions or entire functions such that this is bounded. So this is just a space of entire functions with the controlled Crowe's behavior at infinity. Okay, that's what it is. And since these constants Cn, since they are increasing, the condition of having bounded Cn norm is getting weaker and weaker as larger if n is increasing. So we get a scale of Banach spaces where H0 is just a space of bound holomorphic functions. So these are constant functions, just the complex numbers. And then they increase, and they are all inside F12, the 2 Fock space, because these Cn's are always smaller than 1/2. Okay, and they all have a norm. And the next observation is this. Cn is a group, of course, and it acts unitarily on the 2 Fock space by some weighted translations. So the Gaussian measure is not translation invariant, but if you add a weight, then it becomes, then you can produce a unitary representation of this group. And these are the so-called Weil operators, WZ, which take a function on the Fock space and they translate the argument. And then to make it unitary, you have to multiply with the normalized reproducing kernel. And that's a family of unitary operators, and it's a representation of this group. And with this kind of operator family, these Weil operators, we can form an operator-valued function, which is denoted by alpha z. So it's a function on Cn and has values in the operators by fixing a linear operator and just conjugating it by these Weil operators. And that, in a way, allows you to take the operator and shift it to different places, if you want. And now I say that an operator, a bounded operator on the Fock space, which leaves H, so H was the union of all these spaces which appear in the scale, which leaves this fixed. We call this, we say that this acts uniformly on continuous, on the above scale, if the following is true. If whenever you fix some number n1 in n, you find another n2 larger than n1 and some constant, which is independent of z, such that for functions f in one of these spaces in the scale, hn1, you have this uniform norm estimate. And uniform means uniform in z, so this d does not depend on z. And then we collect all these bounded operators, which have this property, so we call them operators which are acting on the scale. They could be unbounded on the Hilbert space itself. And we call this FL, space of operators acting uniformly continuous on the scale. So I show you a picture. So this is what I mean. We have a scale of Banach spaces, all consisting of holomorphic spaces. An operator is acting uniformly on this scale. Then whenever I fix a starting space, I find another space, maybe far out, such that this operator, after conjugation with the Weil operators, act uniformly between these two spaces. So they have different topologies. And the operator norm should be independent of Z. Or the bound should be independent of Z. That's what it means. So you may think of like a differential operator or pseudo-differential operators acting on scales of Sobolev spaces. That's such a thing. But here's a simpler, we only have scales defined by a growth condition. Okay. So what is clear is that this type of operators, they form an algebra. If you have an operator which acts on that scale, and you have another one, you multiply this, the product still acts on the scale. And it still acts uniformly on the scale. And what one can show is that these operators, which act on the scale uniformly, they contain all Toeplitz operators with bounded symbols. So they have this property, they act uniformly on the scale, and it's important that the symbol is bounded. And it's not an algebra, only an algebra, it's also a star algebra. And the star is the star which comes from the Hilbert space adjoint on the Hilbert space, F2, 1. And the next observation, which somehow relates this to English result, is that if you take now an operator acting on this scale, so you may think of this as a well-behaved operator, then a compactness of the operator again can be characterized by vanishing of the Berezin transform at infinity. And since these algebras contain all Toeplitz operators, and since they are algebras, they contain all finite sums of finite products of Toeplitz operators, but they may contain more, that truly extends the English result to a larger space, to a larger algebra. So now the Toeplitz algebra comes into play. So if p equal to 2, we can consider Toeplitz operators with symbols in L infinity. So these are bounded operators, and typically, if you take two Toeplitz operators and you look at the product, then different from maybe a pseudo-differential operator, that's not a Toeplitz operator anymore. So you can look at C-star algebra, which is generated by these Toeplitz operators with bounded symbols, and that's T. That's the Toeplitz algebra. And the question is, what is that? So here's a place where the Toeplitz algebra appeared in an approach to generalize English theorem to a larger space of operators. And with Israelowitz, we observed that if you have an operator, a bounded operator, then this operator is a compact operator if and only if the operator is contained in that C-star algebra and the Berezin transform vanishes at infinity. So in a way, this extends English result to the largest possible algebra, C-star algebra. You cannot do better in a way. And it also says that outside the Toeplitz algebra, there must be operators which have vanishing Berezin transform at infinity, but they're not compact. And one can write simple examples by hand, so that's not very mysteriously. But in a way that tells you a way to extend the theorem to from Toeplitz operators, finite sums of finite products to the C-star closure. Okay, the story still goes on. The next observation is that this result generalizes to p-Fock spaces. And it also generalizes to all parameters t in the Gaussian measure. So that the first generalization is not very deep. However, we have to assume that p is strictly between 1 and infinity. If it's 1 or infinity, then the generalization doesn't work anymore. And in this case, of course, we do not have a star because they're just Banach algebras. So we're talking about Banach algebras here. Another question is there some relation between the last two theorems? So the first one says that if you have these operators, bounded operators, which act on the scale uniformly in a nice way, then you have the compactness characterization, we have the Berezin transform. And the next one says if you have something in the Toeplitz algebra, you have the same thing. So maybe these results are in a way related. And here's a new approach to the problem, which was given by Israelowitz, Mitskovsky, and Wick in 2015. And this uses the notion of localization. And they defined the notion of a sufficiently localized operator, and it is this one. An operator on the Fock space is sufficiently localized. I think they did this on the Bergman space over the disk as well, or the ball. If there exist the constants, beta c, so beta is between 2n and infinity, n is a dimension of the space. So this is important. And some constant such that these what I call the Berezin or bivariate Berezin transform of A of the diagonal has a certain decay rate. Namely, it decays like C over 1 plus C minus W to the power beta, and beta has to be large depending on the dimension. And this means sufficiently localized. So the kernel is somehow localized close to the diagonal, if you want. Outside it becomes small. And now we can collect all these sufficiently localized operators on the Fock space and I call these A as L, sufficiently localized. And then the next step is we take all these sufficiently localized operators and we form from this a C-star algebra. So we look at the C-star algebra generated by sufficiently localized operators, and this is C-star ASL. And this lies, of course, inside the bounded operators. And here's an example. If you have a Toeplitz operator with a bounded symbol, bounded again is important, then that is sufficiently localized. The kernel has that property, which then means that this C-star algebra contains every Toeplitz operator, and then it contains the full Toeplitz algebra as a subalgebra. So that's might be even larger than the Toeplitz algebra. So before we had this notion of operators which are acting uniformly on a scale of Banach spaces, and there is a relation. So we observed that if you have an operator which acts uniformly continuous on the above constructed scale of Banach spaces, then that's automatically sufficiently localized. So the action, the nice action, has an influence on the kernel. So Toeplitz operator with a bounded symbol is sufficiently localized, but the symbol can also be unbounded, and you still have a sufficiently localized operator. And this, in a way, relates to the Berger Coburn result and the proof there, because one can see that if you have a Toeplitz operator with a symbol in BMO, bounded mean oscillation, which includes unbounded function, then that operator typically is unbounded. But it may happen that the operator is bounded. And if this happens, then it's automatically sufficiently localized, even though the symbol is maybe unbounded. And the proof now is this. It's very simple. So if we take a parameter S between 0 and 1, and then we recall the proof of the Berger Coburn theorem, which gave us an estimate of this extension of the Berezin transform to off-diagonal values, and it was this one. This we had on the slide before. And now we have to use the fact that F is in BMO. And first of all, if the operator is bounded, then the heat transform is bounded if S is large, meaning if S equal T equal 1, because then it's just the Berezin transform of the operator. So we know for some parameter of S, the heat transform is bounded, if it's large enough. But now if S is in BMO, then we know if we know it's bounded for some time, regardless what the time is, then it was bounded before. So it's also bounded for any earlier time, S between 0 and 1. So that uses BMO. So we can choose in particular S to be 1/2, T/2, which is 1/2 in this case. And if in this inequality S is 1/2, then this number is negative. This is negative. But if this number is negative, then you see you have an exponential with a minus something negative here, which is very nicely sufficiently localized. Okay? So then that Toeplitz operator is sufficiently localized, and that's the proof. So the story goes on. It was namely observed that this notion of being sufficiently localized also leads to a compactness characterization. And that's a result by Shah and Cheng, which says if I take an operator in this algebra, which potentially is bigger than the Toeplitz algebra, then this is compact if and only if the Berezin transform vanishes at infinity. Same criterion as always. So that's another candidate, which gives a compactness characterization via the Berezin transform. And if we combine this with the previous result, then we can even extend the whole theory to Toeplitz operator with possibly unbounded symbols, which were not included in English result. And we get as a corollary the following. If you have an operator, A, which is a finite sum of finite products of bounded Toeplitz operators, with possibly unbounded symbols, but they have to be in BMO, not too badly unbounded. Then again, we have the compactness characterization. Then this operator is compact if and only if Berezin transform vanishes at infinity. This corollary has been known before, but only for a single Toeplitz operator with a BMO symbol. This is in a work by Coburn and Lee from 2011. So they just look at single operators. Here we allow finite products and finite sums. So it's a small extension if you want. So then the next result is a theorem by Chingbo Shah, which at the time was maybe somewhat surprising, and he proved this in the Bergman space setting, and he mentioned that the same proof in a way also works for the Fock space, which is true. And it says the Toeplitz algebra is precisely the norm closure. This is the linear closure of Toeplitz operators with bounded symbols. So the Toeplitz algebra is a norm closure of finite sums of finite products of Toeplitz operators. So that seems to be quite large, but his result says it's very small. It's just a linear closure of Toeplitz operator with bounded symbols. And the Toeplitz algebra actually is the C-star algebra of all sufficiently generated by sufficiently localized operators. And now if we combine this with the other stuff, with the previous characterization, we see that all these algebras which we have obtained are actually the same. Everything what we have seen so far is, in a way, the Toeplitz algebra. So if we take operators which are acting uniformly, continuously on the scale, though this is not closed as a C-star algebra, but we may look at the norm closure of this, then that's again a C-star algebra, and that C-star algebra is precisely the Toeplitz algebra, and that precisely coincides with the C-star algebra, which is generated by Toeplitz operator with potentially unbounded symbols, but they should be BMO, whenever the corresponding operator is bounded. And all of this is the same thing. And the proof is just by combining all the results which we have seen previously. So we know that Toeplitz operators are acting uniformly on the scale. So if we look at the closure of this is also an algebra. If you look at the closure of this is a C-star algebra. So the Toeplitz algebra is generated by Toeplitz operators, is also C-star algebra, so by trivial reason we have this inclusion. Then we also know that operators acting uniformly on the scale, they have sufficiently localized kernel. They are sufficiently localized. So they are in the C-star algebra, generated by sufficiently localized operators, which is the Toeplitz algebra. So we have both inclusions, so these are the same. So L infinity is in BMO. Toeplitz operator with BMO symbols are sufficiently localized. So the Toeplitz algebra is inside the C-star algebra of Toeplitz operator with BMO symbols, which are bounded. And these are sufficiently localized, so they are in here. And this result is Scha's result. This is the Toeplitz algebra. So both all these inclusions are equalities actually. So we have a lot of characterization of the same thing, namely the Toeplitz algebra, but some of them are nicer, because if you want to know what is inside the Toeplitz algebra, if you start with the original definition, then you have to find a finite sum of finite products of Toeplitz operators which approximate that. So that's in practice impossible. Okay, but the other, looking at the kernel, for example, and checking whether this is sufficiently localized or not, that's something one could do. Okay? So that's very useful in applications. So here's another one. This relates to the notion of band operators and Toeplitz operators, which appears, for example, if you want to study Fredholm properties or essential spectra of Toeplitz operators. For example, this was done for the P-Fock space in the work by Fulcher and Hugger, and there's of course a lot of other works which are related to this. And maybe I should recall what is a band operator. So we're talking now about operators on the L2 space, not on the Fock space, on the L2 space. And we call this a band operator if there is some number omega bigger than 0, such that whenever I take this operator and I cut it off from the left and from the right with multiplication operators by functions, f and g are bounded functions, which have support with a certain distance, namely the distance should be bigger than omega, so they have distant support, then that product should be 0. So that's some kind of localization property. And then this, the set of band-dominated operators is then the norm closure of these band operators inside L1, 2, and these form a C-star algebra. And here's another observation, namely is this one. If you take a band-dominated operator, this is a C-star algebra, but these are operators on the L2 space. And these operators, they contain the Toeplitz projection. So the projection onto the Fock space is inside that algebra. And also every multiplication operator, that's trivial, every multiplication operator with an L infinity symbol is also inside the algebra. And since Toeplitz operators are product of those, they're also inside the algebra. So that now tells you if you take band-dominated operators and you cut this off from the left and the right by the Toeplitz projection, you consider these operators as operators on the Fock space now, then this contains all Toeplitz operator. It's also C-star algebra, though it contains the whole Toeplitz C-star algebra. That's inside. But in fact, even more is true, namely that this actually equals the Toeplitz algebra. So this is another description of the Toeplitz algebra by cutting off band-dominated operators with the Toeplitz projection. That's another way of localization. And maybe this last remark is maybe not up to date. It seems that for the standard Bergman space over the disk, same thing might be unknown. One inclusion is true to hold. The other one, I'm not sure whether this is known by now. Maybe one of these inclusion is open for the Bergman space. Okay, so in the last 10 minutes, I want to tell you. So I told you several characterizations of the Toeplitz algebra. I'll give you more here now. And now the question is, what is actually inside the Toeplitz algebra and what is not inside the Toeplitz algebra? If you have something inside the Toeplitz algebra, it's very nice because you, for example, have compactness characterization. You can say more about essential spectra. You know that the kernels are very nice in the sense that they are sufficiently localized. But you may ask, what kind of operators actually are far from Toeplitz operators? And a classical question in operator theory, of course, is given an operator, when is it compact? When is it bounded? When is it shut in P class? When is it in one of these ideals? And another question of that type is, when is it in the Toeplitz algebra? And the Toeplitz algebra contains the compact operators, but it's a strict subalgebra of all bounded operators with nice properties. So you can ask these questions for many different types of operators. Here's a list. I will not be able to tell you the answer in all these cases. I want to discuss weighted composition operators, Toeplitz type operators. I will not discuss, and there are some other classes where this question can be actually answered in a very nice way. But mostly I will stick to this first type of operators here. So the problem is this: if you are given an operator from one of these classes, I'll tell you what it is. When is it actually, it's a bounded operator, when is it inside here? When does it have sufficiently localized kernel? And then, of course, there's a more refined question. When is an operator not just in the Toeplitz algebra, but when is it a Toeplitz operator itself? That's maybe more complicated to answer, and if it is a Toeplitz operator, then you may want to know what is the symbol of the operator. So how could you possibly approach such a question? So how can we decide whether a given operator is inside the Toeplitz algebra? And as I said, starting with the definition of the Toeplitz algebra is hopeless. So if I give you an operator and I ask you, is there any family of operators such that finite sums of finite products approach this in operator norm, I think you're completely lost. So you have to use this other characterization. And here's another characterization, which is based on methods from QHA, which is quantum harmonic analysis. And this is maybe found by Fulcher. And it gives a very simple characterization of the Toeplitz algebra, and it's this one. An operator on the Fock space is in the Toeplitz algebra if and only if the assignment from C to this conjugation is operator norm continuous. Usually this is just strongly continuous. But for elements in the Toeplitz algebra, it's norm continuous, and that's a characterization actually.
What's W?
But W are these while operators. So these are in the way shift operators with a weight, so that they become unitary. Okay. So what you do here, in a way, you take the operator and you move it around with the shift, with the translation over the space C, and then you see what happens to the norm. Okay. And the other thing is to use maybe this fact that the kernel should be sufficiently localized. So we may look at the operator, we form the bivariate Berezin transform, which is this thing here, which appeared many times now, and then we can use the following result, which is just a sufficient criterion. So an operator is in the Toeplitz algebra if the following is true: if you find an L1 function on C, so with respect to the Lebesgue measure, such that this function here can be bounded by H, this L1 function, where the argument is z minus w, so the distance between the 2 points is important. So if you find such a thing, then the operator is in the Toeplitz algebra. And here I want to give an example. So I want to look at a class of operators which are studied in the literature, and they're called weighted composition operators and on the Fock space. And these are operators of the following type. So we take psi in the Fock space, and phi is a holomorphic function. And then if we have something in the Fock space, we can compose with phi. That still gives a holomorphic function. And then we multiply with psi. So that's an operator which has a weight, and there's something you compose with, and that's denoted by w, psi, and phi. This class of operators is called weighted composition operators. Psi is the weight or the multiplier, and phi is the symbol of this. And natural question is, when is it compact, when is it bounded, when is it in the Toeplitz algebra? So to answer this question, one assigns to this operator is typically a symbol, which is a function on C, depending on Z, and of course the weight and the multiplier, and it's the norm of the adjoint operator, and this is this very simple function here, this one. And that function tells you something about boundedness and compactness, and this is I forgot from which year it is this result. If phi and psi are chosen as above, then this operator is a bounded operator on the Fock space, if and only if this function here is essentially bounded. That's a simple criterion. A similar thing works for compactness. Typically, compactness means that this function vanishes at infinity, and that's also true. And so here's what you can see from this. It's a simple remark. If this operator, this weighted composition operator, is bounded, and if this multiplier psi is not zero, then this function you compose with must be very special. So it must be just a fine linear function. Okay, if that's the only possibility to produce a bounded operator, where this lambda here is a complex number which has norm smaller or equal 1. And if this is compact, then this lambda here has to have a norm. Okay, this must be absolute value of lambda is smaller than 1. This has to be inside the disk. But now we know when this operator is bounded, and we know when it is compact. So the question is, when is it in the Toeplitz algebra, which is in between, right? Strictly in between bounded and compact. And this is a joint result with Robert Furche and Miguel Rodriguez, and it says this. So if this weighted composition operator is not zero, and if it's a bounded operator, and we know when it is bounded, it's characterized by this function m. And then necessarily, as we saw here, the function phi must be a fine linear function, this one here, where lambda has absolute value smaller or equal 1. And now I assume that lambda is not the point 1. Then we can calculate the distance of this operator to the Toeplitz algebra, how far it is away. And the distance is just the infimum of the norm distance of this fixed operator from all operators in the Toeplitz algebra, and that can be bounded by this number here. Can be bounded by this number. So in particular, you see this. Typically, this is not zero. So these weighted composition operators, in many cases, they are not inside the Toeplitz algebra. So this composing with a holomorphic function is an operation which is far from being Toeplitz in a way, or being localized. And the corollary is this. Now, if the function I compose with is affine linear, lambda has absolute value smaller or equal 1, and it is not equal 1, then if this is not compact, then it cannot be in the Toeplitz algebra. So whenever the weighted composition operator is not compact, it's not in the Toeplitz algebra. And if it's compact, it's in the Toeplitz algebra because Toeplitz algebra contain the compact operators. So typically they're not inside. And the proof just comes from this inequality. So if this is not compact, then this limit is not zero at infinity. And if it's not zero, then we have something positive here. And so we have a positive distance of this operator to the Toeplitz algebra. We can even calculate that. So it is not just not inside, it has even a strict distance. And the corollary is this. If we have a weighted composition operator in the Toeplitz algebra, then there are only two possibilities. Either this operator is compact, then it's inside, or it may happen that lambda is 1, because this case was excluded before. And if lambda is 1, then that weighted composition operator is just a multiple of the while operators which appear in this uniform transformation. And while operators are Toeplitz operators with a bounded symbol. So they are in the Toeplitz algebra. So this rarely happens, so to say. Okay, so I think in the last 2 minutes I will not bother you with the other question, when such an operator is actually a Toeplitz operator and what is the symbol. Just give you some references here which are related. So the first one, the second one here is about this simplified proof of the Berger Coburn theorem, which extends it in a way, and the inequalities are useful in the analysis which I told you on the Toeplitz algebra. This one here contains the result on the weighted composition operators, the last part, and many other classes of operators, also singular, integral operators, and so on. The original paper on the Berger Coburn theorem is this heat flow and Berezin Toeplitz estimates, which also contains a lot of other results which are interesting. Then there is this so-called quantum harmonic analysis and correspondence theory, which is very nicely working for Fock space operators on p-Fock spaces and others. And people try to extend this to different groups and frameworks, non-commutative settings as well. And so this is very useful, gives one of the characterization I've told you. And this one here is also a nice paper, I think, which gives this characterization of the Toeplitz algebra by Shah, which played also a role in the proofs. Okay, so I think with this, I'll give you my the castle in Hannover. This is where the Math Institute is. Thank you for your attention.
Well, thanks to Professor Wolfram. Any questions?
It's very nice.
Yes. Yeah. So, but my office is on the other side. There's a nice park also. Yeah.
One question. The main study is about Toeplitz operators with bounded symbols. The Toeplitz algebra generated by such operators. And one question is, if you consider Carlesson-Fock measures when the generating symbol is a measure, but it produces a bounded operator, is it known if it necessarily belongs to the Toeplitz algebra?
So if you look at Toeplitz operator with measure symbols.
Yeah.
Yeah, I think in this case, this might not be in the Toeplitz algebra. There might be conditions on the measure. I don't think we considered those, do we,
if
in
you
our paper?
suppose, say, positive measure such that the corresponding operator is bounded.
Yeah. So for these cases, there are of course a lot of characterization of compactness, boundedness, Schatten P class, and so on. This is known. Toeplitz algebra. Yeah, I think we have some results on this.
Maybe with the Berezin transform.
Yeah.
We have some result in this paper with Hausdorff operators. Yeah, out of my head, I cannot give you the criterion, but my guess is sometimes they are and sometimes they are not. So if the measure, for example, is not absolutely continuous with respect to the Lebesgue measure, or has maybe some point measures or something like this, then may not be in the Toeplitz algebra.
Okay, and the second question. So you know almost everything about the Toeplitz algebra. And, you have some results about the boundedness, and compactness is also characterized. So the next question is, what is about the spectrum of Toeplitz operator?
Yeah, spectrum, that's a complicated question, I would say, and not so much is known. So what people study more is the essential spectrum. And then there are some good results which in the way you use limit operators and compactifications of spaces. So in a way, one would expect that if you look at the Berezin transform, then you want to, the Berezin transform is a function on Cn in that case. Then the essential spectrum would be the boundary values of the Berezin transform, but the C has no boundary, okay, or Cn has no boundary, so you have to find a good compactification of Cn using Gelfand theory, and then one has to prove, this is a result by Sures, that the Berezin transform extends to that boundary, and the boundary values in a way give you the essential spectrum. And there's some paper by Raphael Hager, for example, where they study this with the help of limit operators, and they push operators in a way to the infinity, to the boundary, and then the spectrum of these operators, the union of the spectra give you the essential spectrum of the operator. So these things are known, but the spectrum itself, sometimes, you know, of course, if you have very symmetric operators, or if the symbol has a lot of invariances, and you can do a spectral decomposition, as in the work of you, of course, and many others, Nikolai Vasilevsky, Sergei, and so on. Then there are very good cases where you can really understand the Toeplitz operator, because you find the spectral decomposition, which makes it unitary equivalent to multiplication operator. But in general, not so much is known about the spectrum.
Still not so much.
I think, so to me, I guess.
By the way, just wait.
No, you first.
Well, you were like, when you were constructing the symbol, you go to the heat flow or something like that, heat transform, you call heat transform. But if you have the heat transform, I mean, generated for an operator, can you come back, like construct like some Toeplitz operators in a general Banach space? You know, because you have an operator, this close may be positive, so you can generate as a zero semigroup. And then the question is like, you can come back to construct, I don't know, the Toeplitz operator and do the similar question or not? Because
so you want to start with a semigroup,
yeah,
and want to do Toeplitz theory. Yeah, I mean, this fact that the heat transform comes as the Berezin transform in this case is a very specific thing, to my knowledge, for the Fock space. So once you go away from this, you will lose the connection to the semigroup property. I mean, even for the Bergman space, you have a very general or very standard weights. Then you lose this connection to the PDE or semigroup property. I mean, if you start with the semigroup, then you have to construct a lot of things to get the Toeplitz operator, right? You have to find the correct Hilbert space. You have to find a quantization map.
You can go to general spaces, because here you are working with mostly holomorphic functions, right?
Holomorphic functions, yeah.
So if you begin with the C0 semigroup, you can speak about Banach space, which is, well, I don't know, just because I saw some estimates, you can do it.
Yeah, you can do some constructions maybe, but here you start with the function space and the very simple and natural operators, and then some flow appears in the analysis. And there might be ways where you can go backwards from the flow, but then you have to construct a lot of things. And to my experience, it really happens that you have such a nice semigroup property in your space.
So Carlos,
No, you first. You first, Alejandro.
Nice talk, Professor. For the other classes, the answer is similar? I mean, the compact operators are the one that belong to the Toeplitz algebra, or?
So the compact operators always belong to the...
for the others. When you analyze, I mean, the Volterra.
Yeah, the answer is it really depends on the class. So whenever you have a class, you have to find some criterion, when it's inside and when it's outside. So another class where you can very nicely describe this are the singular integral operators in the sense of K-Shu. then you can give a very precise criterion when this is in the Toeplitz algebra by some.
It's very different, the analysis.
It's very different analysis, yeah, I think so. I mean, here, if you have an operator, so the very simple operator, you take a function f of z and you map it to the function f of minus z, okay? So you just make a reflection of the argument. That's a unitary operator on the Fock space. It's a very simple composition. And that is far from the Toeplitz algebra. So this kind of composition operators, typically they're not localized, right? So they move things around. So they're not Toeplitz. And others here, they might be closer to Toeplitz and inside the Toeplitz algebra. But in each case, you have to find a good way to decide this, right? And here it's very good because you have a lot of factorization of Toeplitz algebra. So you pick the one that is most suitable for your class of operators, and then you try to apply. So for example, what may work very well is this criteria. You take the operator, you calculate that composition, and then you see what happens with the norm continuity and when it becomes continuous. And that gives you sometimes a criterion on the symbol of the operator, or whatever you have to decide. But it really depends on the class. You have to come up with a new idea every time.
Okay, thank you.
Thank you, Wolfram. Sorry I was late. I had an appointment. My question is, have you seen a mathematical problem or an application where people have an operator and for them it's essential to know that if it belongs to the algebra to decide something?
Yeah, I mean, if you're facing the problem to decide whether, okay, I'm not sure whether this is an application, but in this framework, if you want to know whether a Toeplitz operator is compact, then you would look at this generalized symbol, right? And whether this Berezin transform, and whether or not it's compact, you want to, I mean, that's a function, right? A function is easier to understand than an operator. You look at what happens at infinity, or you want to find out the spectrum or essential spectrum maybe from this function. And that, in a nice way, works if the operator was in the Toeplitz algebra, because then you have all these theorems and tools about it. So if you want to do spectral theory for an operator, it is helpful to know whether or not it's in the Toeplitz algebra. Okay, that's, for example, one motivation to understand this. And then there is what I said, this kind of correspondence theory, where you have certain C-star algebras and corresponding symbols. I did not explain this nicely, but if you have such a correspondence theory, then you can very nicely do or understand operator theory by looking at symbols and the other way around. So that's a passage from quantum mechanics to classical mechanics that works nice for these algebras. So there are several reasons, I guess, why you want to know these algebras.
Thank you.
¿Más preguntas?
My question is, exist functions that belong to BMO, but the corresponding Toeplitz operator is not bounded. Exist good example, simple enough?
Yes, I would say. This typically happens, for example, if you take a BMO function which is positive valued. Then I would say in most of the cases, if the function has only positive values, it's unbounded, and that usually gives you...
With oscillation.
Yeah, if it oscillates, yeah, oscillation obstructs usually. I mean, if you have a function which oscillates a lot, then typically it happens that the operator becomes small. But if you have a function which doesn't oscillate and has a slow logarithmic growth, it's positive and it's still in BMO, then this, I'm pretty sure this function will produce an unbounded Toeplitz operator. Because, I mean, as the name suggests, oscillation, high oscillation produces typically bounded operators, I would say. Yeah. And BMO bounds the oscillation. Yeah.
More questions?
So could you briefly explain the main idea behind the counterexample of the Berger Coburn conjecture? And is there any conjecture of what the largest class of functions is that fulfills the conjecture?
Yeah. I wish I could, but I haven't read the paper in detail. It's a bit technical, I think, as what I saw. So they form a certain limits of functions which are already complicated. But it's not a simple example, it's not a function which you can just write down, I think, in that paper. So as I said, I just got the manuscript, and Louis sent me and said they found a counterexample, and my plan is now to check what it is. I mean, my feeling was it could not be, it's very unlikely to be true, because you should also not just control boundedness of a function at the critical place, also maybe derivatives and some other stuff one has to control. But it's very complicated. Okay, let's say it is not so easy to really understand a Toeplitz operator with a given symbol, except for special cases. I mean, the boundedness or spectrum or so on, except for cases where maybe for the symbol is radial or has some good symmetries. So it's very difficult to come up with counterexample in all operators which you can understand. Then the Berger Coburn theorem is true. And all the standard examples.
Thank you.
The conjecture is true.
Well, if you have more questions, please, after the lunch, you can. Let us please thank again Professor Wolfram.
Okay. So switch this off. Okay.
A lot of questions.
Yeah, this is good.
That's good, yeah.